In general, satellites are used for telecommunication, navigation, and observation of the Earth's surface. And in terms of observation, what we want to see are information regarding the weather, for example, or environmental monitoring, or information for agriculture or oil and mining industries. And in these kind of industries, nanosatellites can give a good contribution so that there will be constellations of these satellites, and in order to be able to obtain a uniform coverage of the surface, to have real-time imaging or capability of communication. We started Microspace in Trieste, Italy in 2002, and here is where we have our headquarters, where we also have a laboratory in Singapore at the moment. A typical big satellite have masses that are at least few hundred kilograms, and they could go until several tons, up to 10 or 15 tons. So these are very, very big objects. Here is the comparison with the nanosatellite, which is a few kilograms of mass, very small, is 10 centimeter until maybe a maximum half a meter size, and is in principle much simpler and much inexpensive to bring it to space. So this is our engineering model of the complete nanosatellite, and we recognize here in this portion of the model the propulsion system. This is mainly the tank of the system, and here is one of the two thruster modules where we have 4 nozzles, and another one is here where we have the other 4 nozzles, and then we have the control electronics, and this area will be filled with other electronics and other subsystems of the satellite, like the power system, the batteries, and the radio. And we have new technologies that we have to introduce and use, like micro and nanotechnologies. And just to talk about the propulsion system, what we need to have is always a certain amount of fuel on board, and this will be a part of the satellite dedicated as a tank in the satellite to contain the fuel. And then we will have micro nozzles to perform the function of the rockets, which are positioned in different points of the satellite to create the torques that rotate the satellite, or the forces that move satellite with respect to each other to change distances and positions. Here we have a wafer of micro nozzles. See, each of these little square is a microchip, and it has one supersonic micro nozzle. This nozzle has a convergent divergent shape, is a channel. At the inlet we insert pressurized gas, and the gas is accelerated, it achieves supersonic speed, and it creates a small force. We talk about forces in the order of micronewtons, between a few micronewtons until a few millinewton, and forces that we can control in intensity and duration. So when we create these forces by means of small pulses of gas, then the force will rotate the satellite, and we can create our own design rules that will lead to optimal shapes of micro nozzle, which means to the optimal use of the propellant in the satellite. This system we have invented and created particularly for our micro nozzle, and this is what we use always for R&D and for calibration of the nozzles. And the function of this system is to recreate the vacuum environment that is in space, and to measure the force produced by the nozzle, by the micro nozzle. When the nozzle is operated, the arm will swing, and the amplitude of the swing is proportional to the force, and we can measure this because we have a laser that is measuring the position of the arm. Then we have outside the machine the same electronic that goes into the satellite, so it's the same electronic that controls the nozzle itself, and a small tank that contains a certain amount of gas, that is the propellant. And by measuring the pressure in the tank, we know how much propellant has been used for each pulse of thrust, and so we can calculate the efficiency. Have particularly interesting performance in terms of attitude control, and we are able to achieve very fine angular pointing and very fine translation relative position resolution. We talk about few arcosecond of angular pointing and few millimeters of linear resolution in the positioning. So in this way you can really have a very tight and precise formation flight of satellites working together to image a target on the ground and pointing on this target while they are flying on top of it with very high precision. Here we show a supersonic micronoser. Is a microfluidic device, and we have improved them by adding the ignition of plasma inside the nozzle, and for larger thrust level, still miniaturized but larger, we have a micro rocket, again with plasma production in the chamber for high temperature heating of the propellant and for a high level of specific impulse, which means much more reduced consumption of the propellant. 400 volts, maximum 120 milliampere. Beautiful.
One, two. Now
This is good. This is good.
now it's about.
This is wonderful.
Okay, this is about 250, 3. Want me to reduce? Let me know when you want me to reduce. Now it's 400 maximum starting. So reduce to 350. Yeah.
Okay, this is how it works.